Hello and welcome to the second supplemental video for ECE 108. In this lecture, we're going to outline the basic concept of induction. We're not going to do any formal proofs or anything like that, but I just want to free up a bit of time so that we can hopefully cover one more formal proof for induction in class. So to talk about induction, I'm first going to use an analogy of dominoes. Suppose I have a finite number of dominoes. Okay, so some number, and we'll just call that number of dominoes n. Let's further make two assumptions. The first assumption is going to be that d of 1 is true. Now, what do I mean by d of 1? Well, d is going to be the proposition, the domino in this kind of order of this list of dominoes starting from here, so 1, 2, 3, 4, ... n, falls down. So if I assume d of 1 is true, so d of 1 is true, then I'm assuming that this domino falls down. The second assumption I'm going to make is an assumption about all of the dominoes. So we'll say for all in, I'll use a different counter, for all k in, formally here, the set 1 up to n. For all of these dominoes, if d of k is true, if the kth domino falls down, then it follows that d of k plus 1 is true, namely the next domino falls. So this statement, if I just color code a bit, this statement here is the statement that if this one falls, then it follows that implies that this one would also fall. Okay, so if I put these two statements together, let's ask a question. Does domino number n fall down? If so, if it is true that the nth domino falls down, how would we know it falls down? So just think about that for a little bit. Do all the dominoes fall down under these two assumptions? Okay, so, well, if you think it through, the answer pretty quickly becomes, well, yeah, they should, right? This one falls down, right? Now, by proposition 2, it follows that this domino fell down, therefore 2 will fall down, right? And now by proposition 2 again, 2 fell down, so 3 falls down. By proposition 2 again, 3 fell down, so 4 fell down. And you could repeat this argument a finite number of times. It might take you a really, really long time. Like if n is, say, 10 to the 100, a Google, it might take a really long time for this one to fall down, right? But eventually, you could prove that it would actually fall down just by saying 1 implies 2, 2 implies 3, etc., right? Chasing out that argument. So we can conclude, in this case, 3d of n. Now, this idea can be extended by assuming I have more dominoes. I don't have just n dominoes. I have n plus 1, n plus 2. I have an infinite number of dominoes. Now we can beg the question, if the first domino falls down and this proposition is true for all the natural numbers, can I then conclude not just d of n for this fixed value of n, but can I conclude for all natural numbers, n, d of n? Can I conclude that all of the dominoes fall down no matter how far down the list you go? So if you think about that a little bit, you might say, well, yeah, I could do that. I could just do the same thing I did before, right? This fell to get up to n, but I just keep going, okay? How many times do you have to repeat that argument to actually prove that 3 follows from 1 and 2, right? How many times do you have to do this? K fell, therefore k plus 1 fell. K plus 1 fell, therefore k plus 2 fell. Well, how many natural numbers are there? There's an infinite number of natural numbers, so you would have to make this argument an infinite number of times. And quite literally, no one has time for that. This is the idea of induction. We make by an assumption that if 1 is true and 2 is true under this case where I have the natural numbers in blue, then it follows that 3 is true. We cannot prove this. The program that you would have to run goes into an infinite loop. It runs forever. But we can assume that it works because it seems realistic. And that's what we're going to do. So formally, let's pull over the mathematical expression and go through it real quick. Okay, so here's our formal little bit of math for this video lecture. We start with the definition of an axiom. An axiom is just some statement that we arbitrarily say is true. We don't prove it, we can't prove it, it's just something we say is true. Now, the principle of mathematical induction is an axiom. Again, it is impossible to actually prove that all the dominoes will fall down, but it seems reasonable, so let's just say, YOLO, it's true. Why not? Okay, so here's how the axiom goes. We're going to let P of n be some statement that depends on some parameter n, and this parameter is going to be a natural number. For this course, the natural numbers n will be the set starting at 1 and going forever. So just 1, 2, 3, 4, 5, etc. Okay, so explicitly, what do I mean by P of n? Like, what's a statement that depends on n? One example of a statement that would depend on n is the nth natural number is even. It's a statement, it's either true or false, and its truth value depends on the value of n. We'll give several examples of statements in class, but that's the type of object we mean here. So now, we're going to assume that, quote, the first domino fell, and mathematically, this is replaced with the statement that P of 1 is true. So this step here is referred to as the base case in our proofs, and generally we'll just say like base case or BC, and then we'll prove that P of 1 is true. Following this, we have second statement number 2. This is our statement that, hey, if the one domino falls, it knocks down the next domino, right? So this formula is going to be the statement for all natural numbers. If P of k, then P of k plus 1. That implication is true. And proving that this statement in quotes, this whole thing here, is true, is referred to as the inductive step. So now, if we prove 1 and 2, this axiom tells us that 3 would then be true. That P of n is true for all the natural numbers. All the dominoes fall down, no matter how far down the list you go. Again, this is an assumption that this works, right? So you can think principle of mathematical induction as a machine. You give it 1 plus 2, and principle of mathematical induction, POMI, outputs 3. So if you can prove these two statements, you get 3 for free. So that's the idea of the principle of mathematical induction. In class, I'll first address any questions that anyone has on the concept of induction, and then following that, we'll spend the rest of the class time going through all of the examples that we can fit in a reasonable manner.